Okay, friends, welcome back. Let's start the topic Fourier series. So, in the previous class, I told you by using Fourier series, we can convert or we can write a non-sinusoidal periodic signal in terms of sinusoid. That's what we can do. Okay. So, first of all, remember Fourier series is applicable only for periodic signal. Fourier series is applicable only for periodic signal. Only for periodic signal. This is the one thing you have to remember. Okay. Next, what is a Fourier series? By using Fourier series, we can write a non-sinusoidal periodic signal. Non-sinusoidal periodic signal. Please make the note along with me. Non-sinusoidal periodic signal in terms of sinusoidal signal. Sinusoidal signal of different harmonics. Of different harmonics. Different harmonics. Okay, what is this different harmonics? We will see that later. So this is actually definition of Fourier series. By using Fourier series, we can write a non-sinusoidal periodic signal in terms of sinusoidal signal. Okay, so that's the thing you have to make a note. Here, Fourier series is applicable only for periodic signals. But the question is, sir, can we write any periodic signal in terms of Fourier series? Answer is no. That means you cannot write all periodic signal by using Fourier series. There are some limitations. What are those limitations? We will see that. So which are nothing but the Dirichlet condition. That means if the signal is satisfying Dirichlet conditions, then only we can write the Fourier series. Otherwise, we cannot write the Fourier series. Okay. So I can simply say Dirichlet conditions are nothing but the conditions for the existence of Fourier series. I hope you understand. So let's see. Dirichlet conditions are conditions for the existence of Fourier series. Dirichlet condition, or we can say conditions for the existence of Fourier series. Conditions for the existence of Fourier series. So we are having three conditions here, three Dirichlet conditions. Let's see. So in GATE examination, they won't ask this Dirichlet condition, but if you write any PSU examination, so they might ask some questions based on the Dirichlet conditions. That means they will give you some waveform. They will ask whether the Fourier series is possible or not. Okay. So then you have to see and you have to observe the Dirichlet condition. Okay. Let's see. The first condition, Dirichlet condition. The signal must be The signal must be absolutely integrable. The signal must be absolutely integrable over one period. Over one period. That means, let's say, mathematically I can show like this. Integral over a period, integration over a period, absolute value, mod x of dt must be less than infinity. If this condition is satisfied, then we can say it is satisfying the first condition. Suppose let's take one example. If you take an example like this, zero t by 2 t, let's say, okay, example. So if you consider integration 0 to t mod x of t dt, that is 0 to t by 2 a dt, finally a t by 2. So is it a finite value or not? Yes, definitely a finite value. So if it is a finite value, then we can say Fourier series is possible. Fourier series is possible. Now let's take another example. Let's take another example. X of t is equal to tan t. X of t is equal to tan t. Tan function. Tan function. Is it a periodic signal? Definitely it is a periodic signal with a period pi. Periodic with a period pi. So let's see how it look like if I draw it. This is the tan function, how it look like. Tan 0 pi by 2 minus pi by 2. So what is the area under absolute value of tan t between minus pi by 2 plus pi by 2? So if you take a modulus, then it will come like this. Then the area under this curve will become infinite. So I can write integral minus pi by 2 to pi by 2 mod tan t dt is equal to infinity. So I can simply say it is violating the Dirichlet condition 1. So if it is violating the Dirichlet condition 1, Fourier series is not possible. So I can write Fourier series does not exist. Does not exist. So what I am trying to say is, even though this function is periodic, but we cannot write the Fourier series because it is violating the first Dirichlet condition. I hope you understand. The signal must have finite number of maxima and minima over one period. For one period. So suppose if we consider one period, in that how many maximas are there, how many minimas are there, if you count them. So if that count will become finite value, then we can say this is satisfying the Dirichlet condition. Suppose if you try to find out how many number of maxima and minima over one period, that means if you consider one period, how many number of maximas, how many number of minimas are there? If you count them, if they will become infinite, then we cannot apply the Fourier series. So the number, maybe it is a less value or maybe it's a large value, doesn't matter. Suppose if the number of maxima and minima are finite number, then we can write, yes, it is satisfying the second Dirichlet condition. That means, let's take one example you can understand. Again, I am taking the same example, 0 t by 2. So if I consider 0 to t over one period, this is the one maxima, one minima, one maxima and one minima. So I can say the number of maximas and the number of minimas are nothing but finite values. So then definitely I can write the Fourier series. Suppose if I take a signal, let's call it as FM signal. Let's say the signal is having frequency which is increasing, like this, more frequency, less frequency, again frequency is increasing. Okay. So how many number of maximas and minimas, if you count them, that will become infinite. So infinite number of maxima and minimas are there. So how many number of maximas are there? How many number of minimas are there? So definitely this is not possible for us. So this kind of wave you cannot write the Fourier series. This is not possible. Okay. Third condition. The signal must have finite number of discontinuities. Finite number of discontinuities. What do you mean by that? Again, I am taking the same example. So if I take over one period, how many number of discontinuities are there? Only two discontinuities. These are the two discontinuities. So if you count how many number of discontinuities over one period, finite number of discontinuities over one period. So in one period, we are having only two discontinuities. Two discontinuities. Then we can say, yes, for this kind of wave, Fourier series exists. Suppose if I consider another wave, which is a periodic, something like this, the step size is keep on decreasing. Okay. Zero, t, 2t, like that. So if you observe carefully, the step size is keep on decreasing. So how many steps we are having? Like infinite steps. That means how many number of discontinuities are there? Infinite discontinuities. So even though it is a periodic signal, it is repeating, but I cannot write the Fourier series for it because it is having infinite number of discontinuities. So from this I can conclude that we are having three Dirichlet conditions. One is, first condition is saying that the signal must be absolutely integrable over one period, and that must have finite number of maxima and minima, finite number of discontinuities. So if these three conditions are satisfied, that means the signal is satisfying the Dirichlet condition, then it is having the Fourier series. That is as simple as that. I hope you understood. Okay, take it. Okay. So that's about the Dirichlet conditions. Now let's enter into the real topic, Fourier series. So actually we can represent a periodic signal by using Fourier series. Actually, we are having three kinds of Fourier series. Okay, three types of Fourier series. Types of Fourier. FS means Fourier series. Okay. The first one is trigonometric Fourier series. Or we can write real Fourier. Real Fourier series. Trigonometric Fourier series or real Fourier series. So, to write this trigonometric Fourier series or real Fourier series, the signal must be real signal. The signal x of t must be real signal. Must be real. So, if x of t is a real signal, by using trigonometric Fourier series, how we can write the Fourier series expression? X of t is equal to a0 plus summation n is equal to 1 to infinity an cos n omega naught plus bn sin n omega naught. Like that we can write an cos n omega naught plus bn sin n omega naught. So here this is nothing but the trigonometric Fourier series expansion. So what is a0? A0 is equal to 1 by t integration over a period x of t dt. So we are finding out the area over a period and divided by period. So that is going to give you average value or DC value. So this is going to give you average value or DC value. DC value we can call it. So this is nothing but area over one period divided by period. Divided by period. Then what is AN? AN can be found by using the formula 2 by t integration over a period x of cos n omega naught t dt. So actually AN is nothing but a shorthand notation of A of n omega naught. So what do you mean by that? Suppose n is equal to 1 means A of omega naught. That means for omega naught frequency, what is the amplitude of cos wave? Means at omega naught frequency, what is the amplitude of cos wave? That's what the meaning of n omega. I hope you understood. So these kind of things we have seen in the discrete time signals also. There we have said x of n is similar to that of x of nt. Okay, so that is what we have seen. Next, bn, which is a short notation for b of n omega naught. So this is defined as 2 by t integration over a period x of sin n omega naught t. Okay, take it. Next, polar form of Fourier series. Second one, it is not a new one actually. It is a derivative from trigonometric Fourier series only. So the second one is polar form of Fourier series. Polar form of Fourier series. So you might know this expression Suppose let's say A cos omega t plus B sin omega t. This expression can be written as R cos omega t plus theta. This expression can be written as R cos omega t plus theta. What is the R value here? Root of A square plus B square. What is the theta value here? Minus tan inverse B by A. B by A. I hope you understood. So an expression is given like this. This can be written in this manner. So if I write in this manner, what is the R is going to give you? That is nothing but root of A square plus B square, and theta is going to give you minus tan inverse B by A. I hope you understand. So in the similar manner, this trigonometric Fourier series can be represented by using that formula like this. How x of t is equal to capital A0 plus summation n is equal to 1 to infinity an cos n omega naught t plus phi n. Now you tell me, first of all, what is A0 is equivalent to? Is equivalent to exactly same as small a0. Now, so by comparing this expression with this expression, by using this formula, let me know what is an, which is root of small an square plus small bn. In the similar way, what is phi n is equal to minus tan inverse bn by an. bn by a. So this is the way we can represent polar form of Fourier series. So remember, this is not a new Fourier series. It is actually derivative from trigonometric Fourier series. So to find out these Fourier series coefficients, these are called as Fourier series coefficients. We are using the Fourier series coefficients of trigonometric Fourier series only. I hope you understood. Take it. Exponential Fourier series or complex Fourier series or compact Fourier series. Compact Fourier. So by using this Fourier series, that means to apply the exponential Fourier series, complex Fourier series or compact Fourier series, so many people think that the signal must be complex signal. No, answer is no. Why? This can be applied for real signals as well as complex signals. There is no boundary like that. Okay, we have to apply only for complex signals, we have to apply only for real signals. There is no such thing. You can apply it for both the real as well as complex signals. So x of t can be real or complex. There is no boundary here. X of t can be real or complex. Okay. So whatever it is, we can write like this. X of t is equal to summation n is equal to minus infinity to infinity Cn e power j n omega naught e power j n omega naught. Okay. What is Cn here? It is also compact form of C of n omega naught is equal to 1 by t integral over a period x of e power minus j n omega naught t. So this is the expression for Cn. Okay, take it. Dividing analysis of trigonometric Fourier series. First one. Let's we can write x of t is equal to a0 plus summation n is equal to 1 to infinity an cos n omega naught plus bn sin n omega naught. Like that we should write. Now observe in this the term a0. What is this a0 indicate? And what is this total part? If I divide this expansion into two parts, one is this part, another one is this part. So can you name what is this part? Can you name what is this part? Okay. Listen carefully. This part indicates DC component. This total part indicates AC component. So can I simply say by using Fourier series, I can divide the signal x of t into DC component and AC component. Yes, I can do that. So this is nothing but the DC component and these are AC components. AC component. So I can simply say by using Fourier series, we can write the signal in terms of DC and AC component. This is the one application of Fourier series, trigonometric Fourier series. Next, in the similar way, second one, again I am writing x of t is equal to a0 plus summation n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Now, listen carefully. So, in a different manner, I am saying this one a0. I am combining these two parts. So, if I divide this expansion into two parts, now you tell me. Here I have also divided the expansion into two parts. So if I divide this expansion in this manner, then that first part indicates DC component, the second part indicates AC component. Okay, that is okay. Now you tell me, if I divide the expansion in this manner, what is this first part indicate? What is the second part indicate? So if you observe carefully, A0, an cos n omega naught. If you replace t with minus t, will it make any difference? It won't make any difference. So I can simply call this part is nothing but even part and this part is nothing but odd part. Yes. So if you replace t with minus t, there is no change. If you replace t with minus t, this will become negative. So I can simply say this is going to give you even part. And this is going to give you hard part. This is going to give you hard part. As simple as that. So I can simply say by using Fourier series, I can convert or I can write the signal in terms of even part and odd part. Yes, definitely I can do that. So I am writing that point by using Fourier series. We can write the given signal in terms of even part and odd part. Even part and odd part. So this is another way to see Fourier. Okay, take them. X of t is equal to a0 plus summation n is equal to 1 to infinity an cos n omega naught plus bn sin n omega. So if I expand this one, so by putting n is equal to 1, n is equal to n is equal to 3 like that, so I can expand it like this: a0 plus a1 cos omega naught t plus b1 sin omega naught t. Next, suppose n is equal to 2, a2 cos 2 omega naught t plus b2 sin 2 omega naught t plus and so on. Like that I can write. Now observe carefully what I am trying to say. Take this first term a0, a1 cos omega naught. By taking these two terms, can I simply say they are orthogonal to each other? Yes, we have seen that a constant and a cos wave is orthogonal to each other. Suppose if I take a0, if I consider this one, then these two terms also orthogonal. If I consider a0 with any other term, they are orthogonal. Next, if we take a1 cos omega naught t, compare with any other signal, definitely they are orthogonal to each other. If you take this one, compare with any other signal, definitely orthogonal. So that means if you consider any two terms in the expansion, if you consider any two terms in the expansion, they are always orthogonal to each other. Of course, I hope you understood. So this is the condition, what we can say, this is the necessary condition for the Fourier series. So if you take any two terms, they are always orthogonal to each other. I hope you understood. So it is a compulsory condition actually. Okay. So orthogonality is the compulsory condition in Fourier series. That is any two terms in Fourier series are orthogonal. Are orthogonal. Okay, this is the one. Next, last one, fourth point. What I am trying to say. Now, let's say if I consider a non-sinusoidal periodic signal, let's call it a square wave. So square wave having some time period. So by inverting it, I can get some frequency. So by seeing that it is having a single frequency non-sinusoidal signal. But by using Fourier series, what we are doing actually, we are converting a single frequency of non-sinusoidal into infinite frequencies of sinusoidal signals. So I can simply say a single frequency is converted into infinite frequency. Only the difference is single frequency is for non-sinusoidal signal and infinite frequencies are for sinusoidal. That's only the difference you have to understand. So, or we can directly say a single frequency is converted into infinite frequencies. That too, they are not any arbitrary frequencies. They are definitely the multiple integers. That means integer multiple frequencies, or simply we can say harmonic frequencies. I hope you understand. So, I can say a single frequency. So in bracket, non-sinusoid is a single frequency is converted into infinite frequencies. Sinusoidal. A single frequency is converted into infinite frequencies, sinusoidal, of what kind of frequencies there? Of harmonic nature. Of harmonic nature.